So imagine we have a block on a table with applied force, but the block is not moving. So first step to solving any problem like this is a free body diagram. So I've got an applied force in this direction. I have a normal force up, and I have an mg force down. And if the object is not moving, or at least not, or accelerating, there must be an opposing force in this direction, we're going to call friction. So in this case, some of the forces in the x direction are plus F applied minus force of friction, not accelerating, therefore this equals 0. Some of the forces in the y direction are going to be the normal force minus gravity, which is ma, and that also equals 0. So what we're going to look at is we're going to look at the friction forces. We're going to spend some time talking about trying to get a better sense of exactly what friction looks like. In some ways, the best way to do this is actually to go, there's a nice simulation that we're going to use. And the idea here is that I have variety of different things, and I'm going to try to aluminum on steel. And what we do is we've got our vernier probe, and we're going to apply a force. And you'll notice that what happens is that the force is applied, the object does not move, and then at some point it begins to start sliding. So there's a couple of things that we should notice. I've done a screenshot of this, and it's going to be on the next slide. So what's worth noting is that, in essence, this is force, and down on this axis, although it says time, in some ways it also looks like the opposing force. That's the force that keeps the block from sliding, right? This is, in essence, the applied force. And then there's, at some point, as time goes on, the force is increasing. Force increases with time, and you see that the opposing force, so this is force applied versus the force that opposes it, it increases. And then it gets to this point where we have a constant force. And although it's not obvious from the video until you go back and look at it, reset, and run it again, that once the object starts moving, it moves with a constant velocity. So that, again, I'll play that one more time. Force is applied, and then at some point the force is constant, and the acceleration does not change. So it's probably worth examining this in more detail, and to do that, what we're going to look at kind of two different things. We're going to look at this point right here, which is F of friction maximum not moving. We're going to learn that this is static friction. So we're going to try to get a sense for what the maximum static friction is, and see what it depends upon. So to do that, we're going to go, and in this case, clearly it's going to depend, I believe it's going to depend upon the surface. So right off the bat, the maximum friction here was around 4 newtons or so, and then it broke loose. So let's do a different material. We're not going to change the mass. We're going to do glass on glass. And this time it was almost 10 newtons before the thing changed. Reset. And now we'll do a third surface, graphite on graphite. And in this case, you'll notice that it's much lower. It's about 2.5, 2.25 newtons. So clearly, it's dependent upon the material. But we're going to actually spend more time, oops, reset. We're going to spend more time looking at what happens when we have for the mass. And the way we're going to do this is we're going to take a measurement, record a value, and then take that value and put it in a data table. I'm going to go to the middle of this, which is, say, 4.25 newtons of applied force for 1256. So what we've done here is we have a mass of 1256 grams, or 1.25 kilograms, and because I'm just at this point just trying to get a relationship, I'm going to call that 12.56 newtons. Now in reality, I probably should use 9.8 as opposed to 10, but for doing the math, it's not going to be a big deal. And if you remember, the static friction was about 4.25 newtons. That's where the thing broke loose. So I'm going to reset. I'm going to increase the mass, 1409. And we'll call that 1409 and 4.75. And 1409 grams, 1409 newtons. We'll do, I guess, maybe 2 more of these. Reset. Increase the mass again. 1660. Hit start. 16660. And that looks to me to be about 5.5 or so. So 1666 and 5.5. So this is about 5.5. This is 1666 grams, or 16.66 newtons. One more data point. Reset. Make it 2 kilograms. Maximum is somewhere in the range of, say, 6.5. So 2 kilograms and 6.5. So 2,000 grams, 20 newtons, and 6.5 newtons for a friction force. And so now what we're going to do is make a graph of force of friction in newtons versus the normal force. So the static friction is going to go from about 0 to 6. And the normal force is going to go from 0 to 20 make that 10, make that 20, make that 5, make that 15. And so our first data point would have us at, so this is just 2, 4, 6. Our first data point is going to be somewhere around here. Our second data point, oh, my bad. Let's see. So try again. Normal force of 12.25. Friction force of 4.5 would be right about there. Friction force of normal force of 14. Applied force would be right about here. 16 and 5.5 would be right about here, and 20 and 6.5 would be right about here. So it's not hard to believe that this is going to be a linear relationship, and we'll calculate out what that is in a few seconds. But having said that, we can calculate the slope of the line, and we'll come back and do that in a second. So we've made measurements of the force required to set the blocks into motion. We call that, that is the force of static friction. And we have compared that to the normal force, basically the force between the contact force between the block and the table. We projected that it was going to be a straight line. I went and put this data into Logger Pro, and sure enough, it comes out to be a straight line. And what I want you to notice is that the slope of this is 0.3, and then the units are newtons per newtons. So it's a dimensionless quantity. So our next step is going to be to do this same experiment, but this time we're going to record the point where the block starts sliding and look at what the friction is there. So what force is required to keep it moving at a constant velocity. I'm going to hit start. You're going to see that graph that we saw before. And remember that for this first set of data, we were interested in this peak value right here. Now what I want to do is kind of record that value right there. And so what I'm going to do is vary the mass, or vary the object's mass several times and record that data. And then I'll take that data and I'll put it into a Logger Pro spreadsheet. So let's look at that. This is the kinetic friction. So again, I've done the same thing. This right here is that first data point that I collected, and then these are the rest of them. Remember that the normal force in this case is equal to mg, and I4 and g really should be 9.8 meters per second squared, but I used 10 meters per second squared because I just want to do I'm just trying to do a comparison. So that data is put into Logger Pro. Whoops. That data is put into Logger Pro, and you'll notice that this time the slope is less. So in this case, we have a slope of 0.2437, so I'll round it off to 0.24. Again, it's dimensionless. And this slope here is an important thing. This actually has a name. This is called the coefficient of, in this case, it's moving, so it's the kinetic friction. And I would write that as mu kinetic is 0.24, and that would be steel on aluminum. And if you go back several slides, in this case, we would call this would be mu static is equal to 0.3. And here we want to actually write this as mu static is less than or equal to 0.3, because you remember that the static friction was only as large as it had to be. So if I'm only pulling with 1 Newton of applied force, sorry, if I was only pulling with 2 Newtons of applied force, then the static friction is only going to be 2 Newtons to counteract that friction. So as we said, a couple of things we've noticed. We noticed that the force, and this in this case would be the friction force. Oh, sorry. Never mind. So a couple of things are worth noting. Notice that that as the applied force increased in the object did not move until the force of friction was basically overcome, and the object starts sliding, the block moves, and then the friction force, the opposing force, remains constant. There are kind of 2 types of friction forces. We said that static friction is equal to the applied force until the applied force is too large. Then the block slides, and the static friction is now goes to kinetic friction. We said that mu static max is typically greater than mu kinetic, but static friction is not a constant, and it's only large enough to balance the applied force. Kinetic friction, on the other hand, is a constant. It does not change, because it doesn't change to first order. The one last thing I want to talk about, or I want to look at, is some free body diagrams. And so in these free body diagrams, I'm not showing the normal force and the gravitational force. I'm only looking at forces in the x direction. So imagine I've got no motion and I've got or no applied force. Then in reality, there are no forces. F net equals 0, and nothing's going on. There's no friction force. Now suppose I apply a small applied force. It's not moving, no motion, and so therefore there will be a opposing force, force of friction static. And these two are going to be equal and opposite, and I've got static because it's not moving. Now, suppose I apply a larger force, but it's still not moving, and therefore my force of friction static is going to be equal and opposite. Force of friction static is still equal to the applied force. Now, imagine now that I have a larger force and the box is accelerating. So there's a couple things I hope that are obvious. One is the bigger applied force. Now I've got force of friction, kinetic, and force applied is greater than the force of friction, kinetic, and I've drawn it such that force of friction, kinetic is less than the force of friction, static, or static max, so to speak. And then last but not least, suppose I remove the applied force, so F applied equals 0, but it's still moving. Well, in that case, I'm going to have a force of friction, kinetic, and these two forces are going to be equal. Force of friction, kinetic, is a constant, so the force that's slowing it down now is the same in this picture where I'm accelerating to the right and in this picture where I'm accelerating to the left.